Okay, let's start. It's a little more difficult after lunch, doesn't it? And so maybe we should have made the lunch worse so that we eat less. Anyway, some logistical things. By the way, if any of you are interested in working with any of the faculty, interested in any of the sort of MTech or higher options, other options, do let me know. What I'm doing is that we're trying to organize one of the tutorials next week. We will organize it as a sort of, we will not have a tutorial there. It will be a sort of opportunities in computer science, IT kind of a session. I'll invite all the faculties, okay, in here, and they'll sort of talk a little bit about the research, because here they've mostly been talking about textbook material. Yes. Yeah, absolutely. Of course. Data science is not the only field in the world, of course. So, so that's what I'm saying. And here you haven't even seen most of the faculty. I mean, you haven't seen Neil Dhara, you haven't seen Manoj, Viresh. There's a lot of faculty in algorithms, faculty in systems, compilers. So all of them will come here, and they'll give a sort of 5-minute spiel each of them. Then we will have an open house about this. So I'm trying to see when to organize this. I want to organize it, a few days before then, so that you have time to interact with them if you want to. There's also another, but there's a dinner. There's a, as in, of course, every day there's a banquet on 15th. Okay, and that's going to be on near 1201. There's a balcony there, nice balcony there. So we will have a banquet there. I don't want to promise now, but there are a couple of other activities I'm trying to see if I can coordinate. It is too cloudy now, but the astronomy club had promised me a session, but they're not being able to sort of do it. It's just that the clouds are here. I'm trying to see, there's a creative learning center that we have, which does a lot of fun things with mathematics using sort of tools and all, using sort of objects that we build. I'm trying to get a session out of them. We will have it, if I can manage it, we'll have it in one of the evenings. So again, promises, let's see how many I can keep. Okay, so and alternate, let's just sort of finish up the PCA part, then I'll see how much I get into the model validation issues. Or if the model validation seems too familiar to you, I will sort of just skim over it and then move to hypothesis testing, right? We can also do that. So that's something I have not seen. So as we were discussing that until now, we've been looking at PCA. We motivated the principal directions as being the ones that preserve the maximum variance. So until now, we have been saying the principal directions So by the way, here's a slight mindset change that you need out here, because see, until now, when we talk about variance, we have been we're almost conditioned to think of it as a bad thing, because you want things with low variance, you want things with zero variance, right? Because variance is something like how much is it sort of going away from the mean, right? So it's not, somehow you're sometimes always conditioned to think of it as a bad thing, but in some sense, what you should also realize that variance really captures also the amount of information. Not very formally, but if a particular feature only has one value for everybody, for all the examples, that feature is more or less useless. And because that feature has the same value for everybody, it's a constant, the variance is zero. So therefore, the variance of the feature, right, also has information about, captures information about the distribution of the feature over all the training data, and therefore about the structure of the data. Right? So thereby variance is not necessarily a bad thing, which is why we are trying to preserve variance out here, because here variance is a sort of sit-in replacement for information. Okay, so here we're going to take the alternate view. We are trying to say that can I try to formalize the subspace question? See, we are still looking at this V question, right? Because from X we want to apply V, and we want to get to X times V. And I want to say that what is the right way of choosing V? we said that, okay, if you want to have the variance of xv to be as high as possible, modulo the size of v to be of the order of d cross k, right? That means that you want to have xv as large a variance as possible, then you need to do this principal components, select this principal components in v. Now we are trying to say is that, let me look at the other question and say that we will find out the difference between x times v and v transpose. I mean x and x v transpose, and we will see what is the reconstruction error. I've already given you hints. There's no surprise here, but let us see how it comes about. There are still some surprises, which is the following, right? That look, there's a bunch of different distance measures, right? How do I measure? We have x and we have x v transpose, which is both of them are of n by d. N by d. This is n by d because this part is d cross d. See, how do I measure the distance, right? I could have measured, and there's a bunch, I mean, as I said, there's a lot of different matrix norms. Specifically, there is this Frobenius norm, which is basically saying that you say that a minus b Frobenius norm square will be equal to summation over ij aij minus bij whole square, entry wise difference, and then a square. The other part, the other one, this quantity will then come out to be, sorry, I'm writing it in terms of e minus b, so not to write it so much, in terms of max of ax minus bx 2 norm divided by the norm of x. So in some sense, what we are saying out here is that you're looking at what a does to a vector, right? Pulls it to a times x. You look at what b does to a vector, and you look at which is the vector that distinguishes a from b the most. If the action of a and the action of b are very different on x, I want to take that x on which these actions are very different. It could be in terms of the norm. Maybe a pulls this vector way out there, b pulls this vector only a little bit. It could be in terms of the angle. Maybe ax is completely orthogonal to bx, right? And I mean, either way, what is the maximum difference? What is the x on which they differ the most? And I'm trying to find that one direction and the amount of difference. So in some sense, and I'm not going to formalize it, but it is true if you think a little bit, and if you come to me, I'll explain later. This you can explain, this you can interpret as basically the average sort of distortion over all vectors. So a minus b Frobenius, you can kind of interpret it as saying that if I had a way to average over all possible vectors, and on an average, the distortion, I mean, and measure the difference over all vectors, difference of the action of A and the action of B over all possible vectors, you would get this A minus B Frobenius. Again, I'm not going to formalize it because that would need me to talk about high dimensional Gaussians, etc. I'm not going to do that now. Ax, this quantity says that it is the worst possible sort of gap between A and B in terms of their action on any individual vector. Okay. And we want to, I mean, the question is that we might want to minimize this quantity. We might want to minimize this quantity. Who knows, right? These are two different measures. Just like we had logistic regression and least square regression and all that. These are two different measures. Now, what do I do? What do I stick to? It turns out that at this point, at least the universe is very kind. The V that optimizes is the same for both. And in fact, very surprisingly, it's the same for a lot of different such measures, right? It's the same for, I'll just say this out loud. It's the same for all matrix norms that are known as unitarily invariant. Basically, if you have a matrix norm, right? Let's say that this is one possible norm. And if you have a property that multiplying it by an orthonormal matrix does not change the norm. There are certain matrix norms for which multiplying by an orthonormal matrix does not change the norm. For all such matrix norms, it's the same answer. Same answer. And which is the same, which is the what we did is in the, I don't know why. Which is the same answer, which is what we saw in the principal components. Okay. Yes. that are unitarily invariant. So yeah. So let me say that A for all Q that is orthonormal, for all A, the norm that is here is so it might seem a mouthful, but invariant means remains the same, and unitary means orthonormal matrix. So unitarily invariant means that under multiplication with orthonormal matrices, the norm does not change. And so it's a nice property to have. For instance, the Euclidean length, that is unitarily invariant. If you rotate the vector, see, multiplication by orthonormal matrix is basically rotation. It's just saying that if you rotate the data, your norm does not change. Right? And it's a nice property to have. And under all such norms, right? The optimization, the solution to this optimization remains the same. The V that you look for remains the same. Okay, so what is that? And how do I get that? Well, I mean, again, we have really done the work. It's just a question of looking at it from the other side. Let's just do that. Okay. So as we were saying that, let us look at the representation of the data in terms of the eigenvectors of the data matrix. Right? I'm saying eigenvectors of the data matrix, not the eigenvector of any individual data point, because that doesn't make sense. Right? Once you give me the data matrix, right, the n cross d data matrix, I'm looking at the principal all the eigenvectors of the covariance matrix of the data matrix, v1, v2, vd, right? And they are pairwise orthogonal. They form and therefore they form a basis of this d-dimensional space. Because they form a basis of this d-dimensional space, and because each data point is d-dimensional only, I can write each data point in terms of these eigenvectors. Right? So let me call these eigenvectors v1, v2, vd, right? And the coefficient of the point, the coefficient, and I'm writing xi, which is ith data point in terms of these vectors, right? And so therefore xi becomes zi1 times v1, zi2 times v2 times plus zid times vd, where each zid or zi1 is really a scalar, right? So, and if I were writing a matrix representation of it, we were representing the x's using the rows of the data matrix, so the xi transpose. And let me write the v's as the rows of this v matrix. So then the zi's become the corresponding row of the z matrix. Let me call this the z matrix. Therefore, I'm writing it as x is equal to z times v, right? Where v has this v1 transpose, v2 transpose, and then x as the data in its rows. And this is, well, I think I have a picture later perhaps. This is n cross d. This is n cross d, and this is d cross d. This is just coordinate transformation, nothing else. Just representing them in a different coordinate. Okay, what is the benefit of this? It's beneficial because it allows me to see what is really happening. Suppose d was equal to 3, right? If d was equal to 3, then I'm writing xi as zi1 times v1 transpose plus zi2 times v2 transpose plus zi3 times v3 transpose. And this is exact. The right hand side is exactly, I mean, xi. That's exactly the point. Okay. So furthermore, each zip, I can say each zip, it's really xi transpose vp. And because if I have a coordinate basis and I have this point, the coefficient that this point has for this particular element of the basis is the dot product of the basis element with the point, right? So that's the zip. Okay, so therefore, yeah, I mean the xi I can always also write it as xi transpose v1 times v1 transpose, xi transpose v2 times v2 transpose, xi transpose v3 times v3 transpose. See, this reminds you of the way that we were kind of looking at before. Okay, let's see. So now suppose, now all that we were doing before is that we were not taking all d of the eigenvectors. We are taking a smaller number of the eigenvectors, right? And let's just say that we were taking k of them. We're taking k of these eigenvectors, and let's say that you calculate this summation sort of xi tilde in terms of the first k of them, and you write zip times vp. The sum over p now goes from p equal to 1 to k. Okay, so this is now my new representation of the data. This is my representation. This is my representation of the ith point. What is the reconstruction error? Now, you're not interested in minimizing reconstruction error, so let me define the reconstruction error. So the reconstruction error now, the difference of xi with xi tilde. They are of the same size. Both of them are d-dimensional things. Okay, difference of xi and xi tilde is exactly the terms that I've left out in the sum, because the sum was over d things, right? And here I have taken here I have taken only k of them. Right? So therefore, from k plus 1 to d would come in the error. So therefore, this is the reconstruction error for the ith point. This is the vector. I have to take the norm of this vector. So therefore, let me take the norm of this vector. Let me sum it over all possible I. This is what we want to minimize. This is the reconstruction. Okay. So now, why is this the same? Why does it give the same value? Well, right? Assume that we have the center of the data is 0. Assume that we have found out mu and we have subtracted from everybody. So now, if you look at the captured variance, whatever we were defining as the captured variance on the first k terms, which is exactly this term, just that for the very nice. Is that we were taking for all, for every p, we were taking the summation over all I, right? Xi transpose Vp square, the projecting the point on the Vp direction, right? And we are taking the sum of these squares, right? I would have subtracted the mean, but I've said that the mean is 0. So therefore, there's no point subtracting it. It would just subtract 0. So, and then I sum over all the squares, and then I sum over all the k possible directions, right? One of these terms, so each of these terms is the variance along the corresponding direction. Variance along the V1, variance along V2, variance along V3, and I've summed this up because these are orthogonal. Okay. Let me just for simplicity, let me interchange the sums. I've taken the sum out here, sum over I out here. I've taken the sum over p less than equal to k over here. Just a simple interchange. Nothing much. It just allows us to compare two things better. Now, right? The total reconstruction error now is again the same thing, right? It was the summation over all I for the ith point, right? The reconstruction is the summation over all p greater than k, because remember I've left those out. Xi transpose Vp square. That's the reconstruction error of the ith point. I've summed it over all possible I. Now, if you look up these two quantities, if you look up the green quantity, sorry, I should not make this. The green quantity and this fluorescent blue quantity, right? They have a nice property, which is that they're really complements of one another. If you sum up them, right, for every I, for each I, this quantity and this quantity, they sum up to exactly the norm of xi square. Because I've taken the first k here, I've taken the remaining k here. So they sum up to exactly the k square, which means that if you want to minimize the first one is the same as maximizing the second one, and vice versa. Right? And that's exactly the reason. That is all. And as I had promised, that the only thing that is going on here is the Pythagoras theorem. That xi, I'm writing it. The only reason I'm able to write xi as the sum of the first one and second one is that the VIs are orthogonal, right? And then by using these orthogonal projections, I'm able to write this out. So therefore, if I were to formulate it using the minimizing the reconstruction error rather than maximizing the variance optimization problem, you would get exactly the same problem. Okay. So now, let us just recap again and let me build a final connection to singular value decomposition. Then we'll look at some examples. So X is again the data matrix, n cross d data matrix, right? What we were, and assume that it's zero mean. So we had captured we had created C, which is X transpose X, which is the D cross D covariance matrix. Right, and the principal components of X are given by the eigenvectors of C. We had looked at until this point. The added twist is that you don't even really need to construct C. Right, I could have just looked at X, and some of you were around the dais asking about this connection. I did not really need to look at C. Right, I could do another decomposition of X, a different decomposition, right, a beautiful one, and I could have gotten the principal components basically from X without calculating C. So whether or not which is cheaper depends. I don't know, because calculating C takes time, calculating eigenvectors takes time, calculating SVD also takes time. Theoretically, they're the same, but it all depends on numerical stability and all these things which you're not really discussing. So what is this? What is this other decomposition? It turns out that there is this very beautiful decomposition. Let me see, is it? Okay, let me just, there's this very beautiful decomposition here. That's called the singular value decomposition. Singular, S stands for singular, V stands for value, and D stands for decomposition. Right. Now, what is this decomposition? See, why could we take here's the basic crux. Why could we talk about the eigenvectors of C? Right? I mean, C was a matrix. Does every matrix have eigenvectors? I can see some heads going this way. So yes, no? Does every matrix have eigenvectors? Determinant? No, you're talking about eigenvalues. So you're saying determinant of, so you're defining eigenvalues as determinant of A minus lambda equal to 0. Right? So if it is a square matrix, if A is a square matrix, it has eigenvalues. It has eigenvalues. They might be complex, because I mean again, going into too much mathematics perhaps, because the reals is not a closed field under polynomials and under sort of finding out roots of polynomials. Therefore, they might not be, if you stick to reals, they might not have real eigenvalues. But every square matrix is guaranteed to have polynomial. Every square matrix is guaranteed to have complex eigenvalues, because you can always find the roots of this determinant. But eigenvectors is a slightly different business. Eigenvector says that the matrix has to satisfy this kind of a property, CV equal to lambda V. That's when V is an eigenvector, right? And of course, square matrix, matrices which are not square, they do not have eigenvalues. They do not have eigenvectors, not even eigenvalues, first of all, because you cannot write down the determinant. But even all square matrices do not have eigenvectors. They satisfy a property known as diagonalizable. It has to satisfy the diagonalizability property, which is, I'm not going to formalize it any further, only then it has eigenvectors. So therefore, I sort of slipped this under the rug. How did I know that I could create the eigenvector decomposition of C? It turns out that C is a very special, worried about eigenvectors, okay. Should I just keep on speaking, perhaps? I think that's it. Okay, so C is a very special matrix because C is obtained as X transpose X. Okay, and these are called positive semi-definite matrices. So C is symmetric. First of all, notice that C is X transpose X. So therefore, C transpose is also X transpose X. So C equal to C transpose. C is symmetric. C is on the top of it. It is positive semi-definite. They have very nice properties. They definitely have eigenvectors, and when these eigenvectors are orthogonal to each other, pairwise orthogonal, etc. Now, if I give you an image, that image is, let's say, 10 by 50, 10 pixels by 50 pixels, not even square. Right? So how will you calculate eigenvalues? How will you do the dimension reduction? You can say that, okay, I'll calculate C from there and do that. Right? But here is another decomposition that is guaranteed to be there for every matrix. for every matrix, you have this strange decomposition. It's a beautiful one. It's called the singular value decomposition, and it has the following property. Okay, that you can write out any matrix X as a product of three matrices. Right? The first one we call it U. Second one we call it sigma. Third one we call it V transpose. This is not surprising. What have I told you? Because let me take V transpose equal to X. Let me take the other two as identity. So this is already there. Okay, let me add one more property. The middle element, the middle sigma, is going to be a diagonal matrix. This is also not surprising because I could put in identity, sneak in identity in here. Therefore, it is not surprising at all. Okay, this has diagonal entries such that all of them are non-zero. Okay. Furthermore, U and V have special properties. This is the interesting part. U and V have properties. The properties are the following: that U, let me write it as U, let me employ MATLAB notation. U dot 1, U dot, let me write it U dot capital K. So U dot 1 means the column of U. I'm using MATLAB notation. So these are orthonormal vectors. Similarly, the rows of V are also orthonormal vectors. Okay, so the columns of U are orthonormal, the rows of U are orthonormal, and furthermore, what you can show is that the columns of U the span of the columns of U equals the column space of A. The span of the rows of V transpose. So the rows of V transpose are the same as the columns of V, equals the row space of A. See, now it becomes strange. So now, okay, that's weird, right? Because now I'm able to write the matrix. If you imagine, I'm able to write the matrix as a product of three matrices, such that in some sense, I'm stripping out the basis for the column space, stripping out the basis for the row space, and all I'm left with inside is a diagonal matrix. Nothing else. There is no other interaction between a column, a basis out here, one basis for the column space and another basis for the rows. The only interaction is that the ith column basis only works with the ith row basis, and the jth column basis works with the jth row basis. There's no other interaction. That is the weird part. That's a very strange thing, right? So, and notice what is happening. Because of this, so these are orthonormal. So what does that mean? Let me just do it slowly. So A, I'm writing it as U sigma V transpose. Supposing I do A times V1. Supposing V is equal to V1 to some Vk. Supposing V is equal, these are the, so then, so these are the columns of V or the rows of V transpose, and we are saying that V1 dot product with V1 transpose any V2 is equal to 0, V1 transpose V1 is equal to 1. They are orthonormal. So let me write it as Vi transpose. Okay. So suppose I take A times V1. What do I get? I get U sigma V transpose V1. Now what do I get if I simplify this? U sigma V1 transpose some V transpose V1. Okay, just rolling it out slowly. Right? V transpose is V1 transpose. And what do I get if I take the dot product? So the first row gives you V1 transpose V1 is 1. What happens to the other ones? 0. So basically we are getting U sigma 1 0 0 0 0 0. So what happens if I multiply sigma with this 1 0 0 0 0? I'm not written the dimensions, but assume that the dimensions are matching so that I can do this multiplication. What happens? Huh? First element. So sigma is a diagonal. So I'm getting u times sigma 1, 0, 0, 0, 0, 0, assuming sigma 1 is the first element. And what is u times sigma 1 times 0, 0, 0, 0? U times sigma 1, 0, 0, 0, 0. Again, we are getting the first column of u picked up. Sigma 1 u1. So a times v1 equal to sigma 1 times u1. Similarly, it would be the case that a times vi would equal sigma I times u1. Exactly the same argument that we were doing. Similarly, what happens if I multiply ui transpose ai, ui transpose a? Exactly the same calculations will happen, right? Because ui transpose a, you would write ui transpose u1 to uk times a, capital K. So this is the u1 to I'll just tell you while I'm writing capital K. So ui transpose u1 to uk. So what would ui transpose u1 mean? I mean, if I equal to 1, let me just write it. Yeah, let me remove the confusion. Let me write it as I equal to 1 out here. So u1 transpose, so this is 1 and everything else is 0. Sorry, this is sigma v transpose. Yeah, because u sigma v transpose and you have rolled it out, sigma v transpose. And again, this is equal to sigma I vi transpose. Sigma 1 v1 transpose by the same argument. See, notice what is happening. Notice, remember these two things. Let me draw the geometric picture of what is happening then. Yeah. So you want to write sigma 1 v1 transpose as v1 transpose sigma, because sigma 1 is a scalar. So then it does not matter if you put it before or after. Yes, you can. Okay, so notice what is happening, and I'll tell you then. So I have a set of orthogonal bases out here. These are orthogonal, and I have a set of orthogonal bases out here. So these are the V1s, V1, V2, V3, V4. These are U1s, U1, U2, U3, U4. There should exactly be the same number of them, U4. So these are all, the blue ones are pairwise orthogonal, the green ones are pairwise orthogonal. So now if I multiply by A, we are getting A times Vi equal to sigma I ui, right? If I multiply by A, each Vi goes to the corresponding ui with some scaling. But see, the set of, so the set of images, you start out with a set of orthogonal bases, you multiply by A, the vectors remain orthogonal to each other. UIs remain orthogonal to each other. They are scaled in length, but they remain orthogonal to each other. Similarly, right, again the same thing, because if I take A transpose, then the role is reversed. You start out with the U's, which are orthogonal bases, multiply by A transpose, you get V's, and again they're orthogonal to each other. That is pretty amazing. Because vectors, typically orthogonal vectors, don't typically remain orthogonal under matrix multiplication. These are special because the way we have found them, right? That these are the only orthogonal bases, right, that remain such that one of them is a basis of the column space, the other is the basis of the row space, and the A acts as a transformation between them. That's the interpretation of the SVD, the singular value decomposition. Okay. Also, there's a lot of there's another very fun fact, which is that, see, we said that sigma 1 to sigma k are all, they're all non-zero, first of all. And these are the k singular values. So number of so the number of non-zero singular values is actually equal to the rank of the matrix. Had nothing to do with rank when I started out, but this property is just like eigenvalues. Number of non-zero singular values is exactly equal to the rank of the matrix. Furthermore, the funny thing is the following. Remember, we had this definition of the Frobenius norm of A. Summation over ij square. Okay. It turns out that this is exactly equal to the sum squared of the singular values. Whether you look at the matrix by looking at all its entries and calculating singular norm, and calculating whether you try to calculate the Frobenius norm by looking at all entries of the matrix, or just by looking at the singular values and summing them up after squaring them, you get exactly the same thing. This is why when you look at physics, when physics people refer to this, they'll say that the singular values capture the energy of the matrix. This is precisely why, because they capture the total norm of the singular values is exactly the same as the total norm of the matrix. That's a very interesting thing. Okay, so these are very, very useful, but let us see the connection. Suppose I calculate A transpose. So what happens? What do I get? If you calculate A transpose, now if you write A in terms of U sigma V transpose, what do you get A transpose to be? Anybody? 2 lines, 1 line of algebra. Write A as U sigma V transpose and figure out what is A transpose and what is A transpose A. Anybody? And what do we get? Just any one of them. Yes. Okay. So, and what else? Only sigma square? That would be very interesting. I multiply matrix by another one and I get back only a diagonal matrix. I don't know. No. AB is not equal to BA. I mean, A is any general matrix. Sigma square V. Okay, close enough. All of these are close. Let me do the calculation. So A transpose, I'm writing A as U sigma V transpose and A transpose as U sigma V transpose transpose. If I do a transpose here, I get U sigma V transpose and I get, so AB transpose is B transpose, AB transpose is B transpose A transpose. Therefore, I get V transpose is V, sigma transpose is sigma, diagonal matrix, and then U transpose. Yeah, V sigma U transpose. So now notice what is V transpose V. This is equal to identity actually, because as I said that V is something by K matrix, right? And the columns of V are orthogonal. The columns of V are orthogonal, then V transpose V is actually identity. And this is identity. This goes away. Once this goes away, sigma times sigma becomes sigma squared. So this you get U sigma U transpose. What does this remind you of? What is U sigma squared U transpose? What other decomposition does this remind you of? This is actually exactly the eigenvalue decomposition. Because U is, remember, U is an orthogonal matrix. So U is actually the inverse of what is eigenvalue decomposition. Eigenvalue decomposition is V sigma V inverse. The V and the V, this has to be inverse of that. This is exactly the eigenvalue decomposition, right? So basically, by taking, I mean, in the U's are actually nothing but the eigenvectors now of A transpose. Similarly, if I look at A transpose A, we'll get back as we'll get this as U transpose sigma V. A transpose A. So V sigma U transpose U sigma V transpose. Yeah. So V sigma square V transpose. So this is exactly the eigenvalue decomposition of A transpose A. So one of the U's and the V's. So U's and the V's are called the singular vectors of the original matrix. The U's are called the left singular vectors because they lie on the left hand side of the product. V's are called the right singular vectors because they lie on the right hand side of the product of this expression. So these are the these are the I don't know why it's jumping so much. These are called the left hand side singular vectors. These are called the right hand side singular vectors. U's and the V's. Again, in case you don't remember, but remember this connection between the singular vectors and the eigenvectors. That if I calculate A transpose, I get one set of and I calculate the eigenvalue decomposition of that comes out of one set of singular vectors. If I calculate A transpose A, I do its eigenvalue decomposition, I get the other set of singular vectors. We actually have one other very interesting property that sort of is staring at you in the face from here. Based on this, what can you say about the eigenvalues of A transpose A and A transpose? Is there anything that you can say about the eigenvalues of A transpose A and A transpose? What are the eigenvalues? Eigenvalues are here. This is the diagonal matrix and this contains eigenvalues. What can I say about eigenvalues then? Something very simple. So for any number x, what can you say about the x square? You can say that all the eigenvalues are non-negative, which is non-trivial. How do you know that? I know that because this is exactly the eigenvalue decomposition. All the eigenvalues of A transpose are non-negative. Similarly, all the eigenvalues of A transpose A are non-negative. Right? That's not an easy thing to say because the eigenvalues, who knows what they are? You have to calculate the roots of this polynomial, and I don't know why would the roots be non-negative. But here's the proof that for these matrices they're non-negative because they are entries of sigma squared, and every entry, any entry, a sigma square diagonal matrix. Therefore, all entries must be squared. Diagonal entries are squared. So they can be known. Yeah. So we had to do V transpose V. V transpose V was identity. VV transpose is not identity. V transpose V is identity because the number of columns is less than the number of rows there, and then the columns are. Yeah. Thank you for the question. Okay, so this is very interesting, and this is very useful because here is what we will do going forward, and I'll show you the application to recommendation systems to a $1 million challenge. Here is something that we can define based on singular values, which is known as the low rank approximation of A. You see, here is another way. I mean, so forget the algebra that we are doing. Here is just another visual way of writing it. See, A we are writing as U sigma V transpose. Here is one other way of writing it. Let me write it A as U1 to UK, sigma 1 to sigma K. So K is the rank of the matrix, okay? V1 transpose to UK transpose. So let me write it in this block form that U1 to UK are the K columns of U, sigma 1 to sigma K are the diagonal entries of sigma, V1 transpose to VK transpose are the K columns of V or the K rows of V transpose. Okay. So if I write it this way, then doing matrix multiplication becomes easy. Then I can write it as basically sigma 1 U1 V1 transpose, sigma 2 I think perhaps this is running out of battery. Okay. See, all I've done is written the matrix multiplication in the following way. Right, that it is equal to sigma 1 U1 V1 transpose. I mean, first I wrote the columns of U as U1 U to UK, the rows of V as V1 transpose to VK transpose, and the diagonal entries of sigma as sigma 1 to sigma K. Right, and then I multiplied it without writing out the entries. So then I can write it as sigma 1 U1 V1 transpose, sigma 2 U2 V2 transpose, sigma 3 U3 V3 transpose, etc. What is U1 V1 transpose? Is that a scalar or is that a matrix? Sigma 1 is a scalar. But what is the thing that hits that sigma 1 is multiplying? The U1 V1 transpose? It's a matrix. And it's a matrix of what size? It's an outer product of two vectors. It's a matrix that's the size of U times the size of U1 transpose and the size of V1, size of U1 and the size of V1 transpose. The size of U1 is equal to the number of rows of A. Which one? No, it's not a diagonal matrix. Why would it be diagonal matrix? Yeah. No, I didn't understand your point. No. So supposing A is n by D. Sorry. Supposing A is n cross D. So the size of each U1 is, so U1 is a vector of length n. And the size of each V1 transpose is a vector of length D. So then this is a matrix of size n cross D. So each of them is a matrix of size n cross D. See, what I have done is that now suddenly this is a different way of looking at A. It's like so think of A as an onion. And all I'm really doing is peeling off this onion, writing A as a sum of these matrices, simpler matrices, right? Along with the weight. U1 V1 transpose, which is also rank 1 matrix. It's just outer product of two matrices. U1 V1 transpose, U2 transpose. I'm expressing A as a sum of different matrices. And it turns out that just like the PCA, you can define what is known as a low rank approximation of A. See, we have written it as a sum of capital K things, right? Suppose I want to say that, okay, give me the matrix that approximates A, right? And that is of the best approximates A, and that is of rank 10. What would you do? You would just take the first 10 terms out here. You would throw away the remaining terms. That's the benefit of this, of these, of this representation. You take the first 10 terms, throw away the rest, and that gives you the optimal. It's optimal in terms of this unitarily, all unitarily invariant norms that I was saying. Optimal in a very, very wide definition. Optimal representation of A in terms of a lot of different norms. Right? Again, we will just questions. First and the best. So I'm not going to. This I'm not going to prove. That's going to take a lot of time. But the connection is the same with the. The proof basically goes the same way as we did the principal component directions. Well, not so much covariance. See, you could look at you could do that. You could take a transpose A, look at that corresponding covariance matrix, and then use the same argument. You could do that. Yes. Okay. So now, what are some properties of A? AK of this AK. So then AK is what? AK then is basically same size as A. Rank of AK is less than or equal to K. So why am I saying that rank of AK is less than or equal to K? And by AK, I mean that you take the top, A10, let's say. You take the 10 terms out here. Why is the rank of this less than or equal to 10? If I take one term, the rank of this is 1. If I take two terms, what can I say about the rank? Rank is not more than 1 plus 1. Because if I have matrix A and matrix B, if I sum them up, the rank of that is less than or equal to rank of A plus rank of B, not more than that. So therefore, if I take, and each of these matrices is rank 1. So therefore, if I take 10 terms out of the sum, right, which is defined as, and that I define as the A10, right? The rank of that is not more than 10. So therefore, the rank is less than or equal to K. And this is optimal, as I said, in a very, very sort of wide range of things. But for all these norms, you can say that A minus AK, let's say Frobenius, you'll be able to say is less than or equal to A minus B, Frobenius, for all possible B of rank less than or equal to K. That out of all possible B, right? That if A is a data matrix, out of all possible B of small rank, this is the one that approximates, that is the closest to A. That's the optimality property. That's the one that I say that I'm not going to prove this. That's going to take a lot of time, but that's the optimality property. Okay, so that's very useful. What is the storage that is needed? If I want to store AK, how much storage did I need? So to store A, I needed n cross D, floating point numbers. To store AK, what could you do? NK cross TK, so that would be ND K square. No, what do you mean? So what does that mean? A with subscript of K, N with subscript. Acha. Sort of, yeah. I think you're at the right. You're so knocking at the right door. Let me just try to sort of elaborate that answer. What you're trying to say is that look, in order to generate AK, you needed U1, U2, UK, You needed sigma 1 to sigma k, and you need V1 to Vk. These are the things that you need to generate AK. Right? Once you store these things, you can generate AK. So of course you can store AK, and that would again be n cross D. But you could store these things, and that would be enough to generate AK. Now these U1 to UK takes space Kn. The K of them, each of them dimension n, therefore takes space Kn. Sigma 1 to sigma k takes space K. There's only K scalars. V1 to Vk takes space K times D. So therefore it is, what you wanted to say was n times K. Nk plus K plus Dk. And that could be much, much smaller than Nd. Imagine n equal to 1000, D equal to 1000, and K equal to 10. So here you have 1000 cross 1000 versus 10,000 plus 10,000 plus 10. So 20,000. Right? 1 million versus 20,000. Okay, and that's a huge amount of storage. There are caveats. We'll come to some of these caveats. So, but before that, let us see some pictures. So here's a picture. So this is a model. Her name is Lena, and this is a very standard picture in computer vision. The original picture is 512 cross 512 pixels, right? And therefore the number of floating point number of bits that you need to store this is 512 cross 512 cross, let's say, the grayscale image. If you are storing, let's say, 16 bits per pixel or something, or 8 bits per pixel. 512 cross 512. Let's just say that. So what we have done in the next one is that we have taken the singular value decomposition, right? And out of the singular value decomposition, we have kept only the first 256 singular vectors and the corresponding singular values. Remember, we were saying that we had the sum, right? We had this sum, and in this sum, we have stored. In this sum, we have stored only this, or this full sum had 512 terms. We have stored only the first 256 of them. And we have reconstructed that image back. So we have created AK. We have reconstructed that image. You don't see much of a difference, at least to the visual eye, there's not much of a difference. Let us go even further. Next image, 128 terms. Next image, 64 terms, 32 terms, 16 terms. Still, it retains a very significant fraction of the image's sort of quality, right? You're able to understand, even at k equal to 16, you're able to understand what it is. Let's say at k equal to 32. What is your, how much fraction are you, what fraction is this storage versus k equal to 512? For this one, as a percentage, what is the storage bits in terms as a percentage of the full one? Hmm? 512. Okay, that's a good point. So the original image, let's just see, the original image is 512 cross 512, and the new image is 512 cross 32 plus 512 cross 32. So n cross k plus k plus k cross n. So therefore, it's basically so this 512 cancels out. So it's 64 by 512. That is the fraction. This 32 plus this 32. Right? I'm ignoring this one. Yeah. Plus 32 does not matter so much. So so this 64, that's about what? 8, 1 by 8. 1 by 8. We've reduced the memory requirement by a factor of 1 by 8. It's a huge saving, right? And still, sort of, if it was object recognition software, it would still be able to detect that that's a person. And that's pretty significant. Let's see some more examples. Okay. And we will sort of do more of this in the tutorial. You will write some of this code. Okay. Yeah. So D was the, I mean, N cross D was the original data matrix, right? The N was the number of points and D was the number of dimensions. So N times D was the total number of bits you had to store. I mean, ND times the floating points data size, etc. was the total number of bits you had to store. Right? Yes, but it is, right? Because now we are storing N times K, right? And we are storing K times D. So N times K plus K times D versus N. Then it will be small. Exactly. That's what we're saying. I mean, again, but you have to realize that you cannot make K to be very, very small. I cannot, I mean, we'll just see what happens when you make K to be equal to 1 or K to be equal to 2. What happens to the visual quality? Let's just see some images. So again, I'll share this notebook. The initial part of the notebook, I mean, is just introduction. Let me just run this, some of these cells. Oh, by the way, all these notebooks, I should give caveats. I mean, a lot of them I have taken, I mean, Google had a course I have, and they're free on Collab. So some of these course things, and then I've modified those a little bit. But they're not entirely produced by me. So, okay, so I'm running this. Let's just see. Yeah. No, D is 512, N was 512. See, we are looking, now we are looking at an image, and so the notation is now a little different. So an image, and here we were looking at an N cross D matrix, but the image is 512 cross 512. So basically, you can think of each row of the image as the data that we are talking about. But basically, we have this 512 cross 512 matrix. We calculate the SVD of this one, and we represent this as, we approximate this as 512 cross 32, 32 cross 32, and 32 cross 512. This is the U, this is the sigma, this is the V transpose. If you store this, then the storage required is 512 cross 512, because you have to store each of these cells. If you store this, the storage requirement is 32 cross 512 plus 32, because this is diagonal, plus 32 cross 512. So basically it is like 64, almost 64 cross 512, if we ignore this part compared to that. So as compared to this, you have to store this one. Yes, which is a factor 1/8 already. Questions? Yeah, please. Which one? 39. Okay. Scale is scale. Yeah. No, that is just the property of A, right? See, what this says is that so okay. So there's a dual, there's sort of a little bit discontinuity here if you want to get down to it. See, when we represent an image by a matrix, we don't think of the matrix as a transformation, right? There we are using there are two different views of a matrix. One is that it's just a square collection of numbers, period. It's just a collection of numbers. You have a rectangular array, it's just a collection of numbers. That is all. That's one view of a matrix. Another view of a matrix is that it is a transformation, what you have learned in linear algebra courses, right? That you multiply, you use the matrix to transform a vector to another vector. What I was talking about in this the SVD, the motivation of the SVD comes from this transformation view of the matrix, right? And what I said about transforming U to V, it's saying that this matrix that exists has this kind of properties. It transforms, this is an orthogonal basis, it transforms it into that, and it scales along with each transformation, but it maintains the angles to be orthogonal to each other, right? It captures the transformation view of a matrix. I understand that there's that it's little bit, it's not obvious that how to think of an image as a transformation, right? But I mean, I don't know if I can give a good explanation for that. But while we are developing SVD in term by thinking a bit about a transformation, it works also in settings where you're using the matrix basically as an array of NumPy array of numbers, right? It works there. Yeah. Well, I mean, this is a diagonal. So I only need to store the diagonal entries. Why? I mean, if I remember, yeah, it just needs a sparse matrix, sparse diagonal, sort of use a NumPy sparse or something, and that would only be there. But even if it is, that would not be significant compared to 32 cross 5. Anyway. Yeah, no, it is. I agree. See, I mean, these optimizations typically happen at the software level. So you don't even, when you use NumPy, it automatically sort of uses a sparse way of storing if the matrix is sparse, right? Sometimes if you apply the right optimization. So therefore, that's why I was not really talking about it at that level. But then there's a caveat that you brought up that is quite interesting. We'll sort of come back to that. That the discussion that you brought up automatically talks about a particular sort of caveat, drawback of SVD. We'll come to that. Okay, so now we have done the connections of SVD with this. Okay, yes. Time taken. That is interesting. The time taken to compute is not small. The time. Mixing up my tools. The time taken to compute SVD is that if it is n times d, right? It is n times d times minimum of n and d. Right? That's the time taken to compute. So nd times minimum of nd. I'm just being a little too pedantic. Just think about, I mean, it is pretty high. It is pretty high. Right, so there are sort of a lot of research in trying to get things that are close to SVD, but much faster, much faster. In fact, I mean, we also work on things like this that you could. I mean, there are tools which are not by us that you could compute it in time taken to basically read the data. Basically, linear time. You could get something that is very close to SVD. Now, I mean, proportional to the number of non-zeros in the data matrix. But okay, we will not go there. That is, if you want those things, talk to us later. So now, so before we do this, I wanted to show you some pictures. So now you have seen this picture. Let us see some of these. Okay, we have time. Yeah. Any questions from the online audience, by the way? Okay. Okay, so we'll share the notebook. Please go over it. The first part of the notebook is basically a discussion of what we said. And let me load up some data sets. So what we're doing is that there is a bunch of data sets. There's an image of a cat. There's an image, some astronomical image. Astronaut, there's some camera, there's some coin, some clock, blobs, coffee, etc., etc. Loading up all of this, and then using the SVD in Python. And this is what we are talking about. That here, this is the space that is we're using to store. We're using instead of n times d, we're using k times m by n matrix. That's why they're writing k times m plus n plus k. Okay, and then they will reconstruct it. So we will see what is the effect of different k. So the compression, this particular function is exactly what we were discussing in mathematics and the mathematical things, taking the SVD and then sort of plotting it, showing the final image. Okay, and then there's an interactive widget to clear this. So now let us interact with this a little bit. So now suppose you take the image of a cat. So let us see it at the highest value of k. So this is the cat. This is the original cat. Okay, and now see these are the this is the eigenvalue plot, similar to the elbow plot that somebody was mentioning. Basically, the x-axis is the number, and the y-axis is the singular values, the magnitude of the singular value. The x-axis is the singular value, this thing, the ID of the singular value. So now, by looking at this, you can already see that, look, there's only a small number of singular values that are pretty high, right? Starting from index 0 to perhaps index 10. So that means that I could potentially throw away most of them and possibly retain the cat. Let's just see. Let's just choose k equal to, let's say 100. So from 180, I went to 100. The compression ratio is now 58%. My new image is 58% of the original image. I can still understand the cat. I went down to k equal to 59. It takes a second to compile. So the new image is 32%, still a cat. 38, 21%, still a cat. 10. Well, it's becoming like that Cheshire cat, this Alice in Wonderland. It's vanishing out slowly. Still possibly, but the new image is only 5%. Now you cannot really see much. So k equal to 1. This does not really preserve the image, right? So basically, that's your question, right? That this is a lossy decomposition. You have to be, if you want to use it in your pipeline, you have to be able to say that, okay, that this amount of loss is acceptable to me, right? That at this loss, my remaining pipeline will still function properly. And we will share this. Please feel free to play around with this. There are a few other such things, and please play around with this. There are color images, compression, and the same kind of things. You shouldn't waste too much time. Okay, so okay. So let me give a couple of more examples. I find this very interesting. That's why I want to talk to you about this, and then some preparation of, we'll come back to how to use for regression methods. Right? This principal component analysis versus genetics. What do we know about biology? When was the last time you had a biology course? 10, right? Yeah, class 10. Imagine when class 10 was for me. So, okay. So, but I mean, this basic thing you all know, right? That we all have genes which basically encodes all the genetic information that we have, and therefore, so everything, a lot of that. I mean, there's of course the question of genes versus nature versus nurture. How much of me as an individual comes from the genetic information inside me versus how much from the environment that I've faced, etc., etc. But these genetic variations are very useful in characterizing populations. So I should just a little bit more terminology. What I should say is that not all of us have the same genes, of course. I mean, they're basically the same, right? But there are mutations that have happened, right? In sort of in your parents, in my parents, in you, in me. Everybody has some mutations that keep on happening, and these mutations are called SNPs, SN, single nucleotide polymorphisms. Why single nucleotide polymorphism? Because this is a mutation on a single, this ATGC. Think of gene as a string of letters. Biology is basically computer science. So, I mean, it is. All of this is information, all of this is strings, and I mean, whatever is happening inside is computation. Okay, so yeah, you're nothing but a Turing machine. So basically, we look at these people in this Nature paper, pretty old. They looked at these single nucleotide polymorphisms in a whole lot of European sort of sample population, 36 countries. So basically, what they have done is that they've collected this matrix. Now we are immediately back to CS. They've created this matrix. Every row of this matrix is a person, right? Is a gene, and the y-axis are basically the locations of where the mutations have happened. If you think of your gene as a string, I could say that in your gene, there's a SNP or a mutation that has happened in this particular location from the standard human genome. Okay. Too many mutations become an X-man. Okay. So that is this data, right? That every row represents one of these 3,000 samples. Every x-axis, every column represents, a location of a single nucleotide. Basically, map out all the locations and see that whether this person has a mutation at this location, right? That's and also some values that perhaps I don't remember whether this is 0, 1 or just something. So this is okay. So now what you do is that you take this and then you take the first two principal components. It is the first two principal components of this matrix. Okay, this is this has to be singular vectors. The first two singular vectors of this, right singular vectors of this matrix, or rather the left singular vectors, because they are of size the number of rows of the matrix. It's a two-dimensional thing now. So it's because there are two vectors. Now multiply this matrix with the first singular vector. Now you get a point location for every row in this vector V1. See, multiplying A with V1 is basically multiplying every row of A with V1, right? A1 transpose V1, A2 transpose V2. So basically, for every row, you get. I mean, if you think of V1 and V2 as the two axes, for every row you're projecting into V1, for every row you're projecting into V2. You're basically projecting this on the two-dimensional plane, specific two-dimensional plane. A two-dimensional plane that is obtained by the first two principal components. You do this, right? What do you expect? I don't know. Then they overlay this on the map of Europe. Okay, this is the left-hand side, right? At the principal component, the two arrows that you see, principal component 1, principal component 2, right? And the dots that you see is basically the location of each of these 3,000 points, right? Because if each of these 3,000 points, have represented them in 2 dimensions. Location of the 3,000 points looks surprisingly like the map of Europe. The clustering is exactly like the map of Europe, which basically means, right, that the samples that we had taken, right, if you think about it more, it's natural, because let's say all the Spanish populations, they have a common ancestor which is closer than, let's say, a Spanish and Italian person, right? So therefore, their mutations will be similar than if you compare the mutation data of a Spanish and a European population. Spanish and Italian person, right? And only the first two principal components is able to bring this out exactly, almost very clearly. Because if you see that, it's pretty close to the map of Europe. Pretty amazing. Okay, and they did some more plotting, etc., and they showed that even inside these countries, you see subpopulations that are breeding more closely than others, etc., and based on this, they could even sort of predict based on clustering of clustering of this data, they could even predict the country boundaries to some accuracy, okay, to some reasonable accuracy. Pretty amazing. Okay, so let's do any questions. Let's do one more example, and this is an important example because you're going to see a real world person talking about this, as if you're not real world, talking about this tomorrow in the business context. Okay, anybody heard about the Netflix competition? Yes. What was the Netflix competition? You could explain to us loudly. Huh? Basically. So basically, see, how does Netflix make its money, really, or any such system? How does Amazon make its money? It's by recommending you the right things to buy, basically, right? Not by, I mean, Netflix subscription gives them some money, but why would you pay for Netflix subscription? Because they're recommending you the right things, right? So the basis of their business is a recommendation system, right? Which says that if I look at your existing sort of content that you have consumed until now, can I recommend you, how well can I recommend you the next thing that you're going to consume? Right, in Amazon Prime, whether it's the next shirt that you're going to buy, or in Netflix, whether it's the next movie that you're going to binge on. Okay, so and what Netflix did was that to release exactly this data. They say that look, let us release a huge data set, right, that has a bunch of users, a bunch of movies, and the ratings that some of these users have done some of these movies. This matrix is not complete. I don't know, because this matrix had like 1 million users, and let's say 100,000 movies. It's a huge data set, right? And even if 1% of the data of the matrix is filled up, that's a very large data. So what do you want to do? You want to say that what they said is that for this user U, right? You know the rating of on movie number 2, on movie number 3. I want you to predict I want you to predict the rating that the user U is going to give on this other rating. Maybe I know the rating on Harry Potter 1 and Harry Potter 2. I want you to know. I want you to tell me the rating on Lord of the Rings. Okay, that's what the problem is. And they said that look, we have our algorithm. You're making money out of it. If you can do it better than, which is if you can achieve an accuracy which is 10% more than our algorithm at this stage, we'll give you $1 million. Yeah. All of them have some recommended system or the other, multiple of them actually. No, very good question. See, what we are saying, what we are looking at is an abstract, a clean version of a recommender system. I think in tomorrow's talk, Rishabh is going to tell you more about how do you detect this when you don't have enough data yet, as in viral. There you have to look at the features. You have to look at, okay, others with similar features, other such videos with similar features, how did they go viral? You have to extrapolate from there. There it becomes much more complicated system. But at the basis, this is what the cleanest problem, sort of abstract out problem is, right? That you're given this matrix, you're given some entries of this matrix, you have to predict the missing entries. Okay. And in this $1 million, if you look at the top 10 entries, the top 10 people who were at the leaderboard, this was running for more than a year. All of their solutions are modifications on top of this SVD base solution that we'll mention. Okay, so we'll just mention the basic, the very sort of brief idea. Okay, so we're given the rating matrix. It's a matrix. See, it's not a square matrix anymore. It's a number of users plus number of movies. Presumably the number of users is much more than the number of movies, but doesn't matter. And likely not all full. In fact, most of the entries are missing. Right? Can we fill up the missing entries? And if I could fill up the missing entries, but before somebody as a data scientist asks you to fill up the missing entries, you should ask your manager, what will you do? Okay, I fill up your missing entries. Now, what will you do with the missing entries? What will the manager do? How? Which movies? Hmm. 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 So basically, just to nail down again, what we are saying is that suppose for a particular user, I have 10 movies, 10 ratings that I've observed. Now, if I can observe all the other predicted ratings, what I would do is take up, let's say, the next 5 movies with the highest predicted rating, and I would recommend them. Right? Pick up the next movies with the highest predicted rating, and I would recommend them. Right? See, notice the framing, because this is going to be important later. What that also means is that what I really need to get correct right, are the highest predicted ratings. Lowest ones, I don't care so much, lower ones. We will come back to that as an issue later, as an issue in this video. So how will I, so that is my business strategy for now. As of now, what we are saying is that trying to fill up all the missing entries. So what would you do? Any suggestions? Suppose, imagine now I have not given you much data. I've given you only the names of the movies and maybe some basic demographics of the user, or maybe no demographics of the user. And I've given you this matrix, some strategies. What would you do to fill up this matrix? Let's say you do. Acha. Okay. So if you have additional features on these movies, then you want to build a model for this particular entry based on learning these features. That is true. Suppose I mean, for now, let us just because we can always add in that part, right? Out of the rating matrix itself, how can you utilize it? If I don't have those features, out of this basic rating matrix, what can we do? Yes. Oh, that's a good point. Actually, I didn't say what this matrix says. So okay. So again, see, we are presenting you a very sort of bare bones problem. Here we are saying that the user has just rated the movie. But of course, when you look at Netflix, they have many such matrices. They have sort of say that how much time the user has watched the movie, sort of, and so on and so forth. Has he or she watched like 10 minutes into this? Has they watched this multiple times? All of that. So we have that data. Let's see. And secondly, right, if you were to kind of take this real world problem, right, and make it into a data science problem that you can actually solve, how would you set up your data? How would you set up your metric? So think of the transition. We're always talking theoretically, right? But think of tomorrow going to a particular company, let's say chat, and them, their manager telling me that, okay, sort of give me good recommendations. How would you set up the problem, the data to learn your problem, to learn your model? What is the data they would collect? What would you set up as the training data? What would you set up as the test data? Yes. Very good idea. That's a great idea. That's a great idea. It says that look, I mean, can we somehow think of a questioning of the users in terms of user types, right? And maybe if I could sort of, by looking at this matrix, if I could put the users into this user types, and maybe I could also somehow group the movies into this movie types, maybe I would be able to say something, right? That's exactly what we'll do in terms of this, in this framing. What we will say that, look, first of all, I mean, there has to be an inherent, I mean, when we come up with a model, I mean, of course, if you think about it from this worst case setting that you do in your data structures and algorithms problems, you won't be able to solve this problem, right? Because if the matrix can be anything arbitrary, it is anything arbitrary. You won't be able to solve the problem. So there has to be some, I mean, in machine learning, there has to be a modeling assumption that says that the data is IID, it follows some simple models, etc. Let us take this user type notation. And let us say that, look, here is my way of thinking about the world. It says that look, there are certain sort of flavors of movies. Maybe there's romance, there's sports, there's drama, there's horror, there's courtroom drama, all of that. And let's say every user, let me generalize the suggestion a little bit. Rather than saying that he or she belongs to only one user type, let's say that I can assign a vector to that user. It says that this user 0.1 fraction sort of the time she likes to spend on romance, 25% on sports, 30% on drama, etc., etc. So this is a vector over an unknown set of, so I don't know what these types are really. They'll come out of data. But there's unknown set of categories, and every user I can think about it as every user spaced, I can think about it as a distribution over these categories. Okay. I don't know what this distribution is. This will come out of the data. Everything will come out of the data. But every user I can think about it this way. Furthermore, every movie I can also think about it in this way, because maybe I don't know. A lot of the Rings movie is mostly fantasy, maybe some romance, maybe some horror. I don't know, right? So let us try to do it that way. So basically, what we are trying to say is that let us think about sort of, this is called a latent space. Let us think about a latent space, right? Which is a space of categories, right? And let us think about every user as being a point in this space. Think about the dimensions as being the sports dimension, the sort of the romance dimension, the drama dimension, the horror dimension, etc. So every user is a point in this space that expresses his or her, I mean, what they like. Right? How much do I like each of these categories? Okay. Every movie is also a point in this space. So Andhadhun lies here, Harry Potter lies there, Star Wars lies here, etc., etc. So I don't know these embeddings. See, we are moving towards representation learning. So we don't know these embeddings, but I'm saying that there is this embedding. Suppose there is this embedding for a user, there is this embedding for a movie. And now, but how do these embeddings relate to the actual data? Right? Only then I can find out, I can go back from the data to these embeddings. So my modeling assumption goes from the embeddings to the data, so that in my algorithm I can look at the data and figure out what the embeddings are. So here's a natural way. Right? So we don't know what this latent space is. This is the fancy name for this. We don't know how it relates to ratings. That's what we have to figure out now. So here is a natural way of thinking about it. That suppose for each rating of the user and for a movie, it is generated in the following way. That if the vector of the user and the vector of the movie have a high dot product, we think that the user is likely to give a high rating to the movie. The interest of the user matches to the category of the movie, right? So therefore, my generative model, this is called a generative model, right? For the rating matrix is the following, that you take the user vector, take the rating vector, take the dot product, add some noise to it. You always add noise to the data, noise to the generative model. This is how I think that the rating matrix has been generated. So now my setting is the following, and I'm saying we are given this. See, we're not given U, we're not given M. We are given these values, some of these values. And we are saying that these values are generated in this particular way. Now you tell me, for instance, here's the following, right? That suppose this is this vector and this vector. If this is the rating, this is the interest matrix of the user. This is the category matrix of the movie. Maybe I took the dot product of these two and then added some noise to it, right? By adding some noise, you can also think about by flipping a coin according to this probabilities, all of that. I'm being vague in there. By adding some noise to this, you get this rating. Similarly, for this other rating, perhaps for this rating, perhaps you took this vector and then you took this vector and then you took the dot product of these two, and then you added some noise, you get this. Yes. Well, this noise is just a modeling assumption, because see, I mean, because the ratings are, let's say, in the range from 1 to 5. The ratings are not arbitrary numbers, right? Just like in coin toss, you observe only 0 or 1. You don't get to observe the actual probability of a head. So therefore, I can say that the observations, the 0, 1, is basically noise added to the probability. That's the same thing out here, right? You're saying that perhaps you're tossing a coin with these probabilities, right? And that 1 minus p and then minus p, that is the noise that is being added. That's what we model as the noise, right? But good question. Because see, if we were actually observing if RUM is exactly the dot product of U and M, then things would have been very simple. But real world is not that simple. That's why the noise is included in the model. So now, this is the modeling assumption. Now, what we are given is this matrix. We are not given this. We are not given this. Given this matrix, this rating matrix, would figure out what is the best fitting W, matrix W, which is the left-hand side, which is the category matrix of the movies. What is the best fitting interest distribution of the users? We have to find out these two. Does it look like a problem you have already solved in this class itself? Right? Because if I could figure out these, right, then see, the benefit of figuring this out is that for this missing entry now, right, I could take the predicted interest vector here and the predicted interest sort of category vector of the movie, and I could take the dot product and I could predict the rating. I could predict this question mark by looking at the red column in the H transpose matrix and the red row in the W matrix, and by taking the dot product. I could easily do that. So therefore, therefore it makes sense to figure out these missing things. It's like fitting a model. So how do we figure this out? What does this look like? You're basically writing the matrix R as this W times H transpose plus noise. That's how, and we want to suppose we say that we will have k less than equal to 10 categories. I think that 10 categories is enough for quantifying number of movies. Therefore, what are we saying? What is the best rank 10 approximation? What is the rank 10 factorization of the rating matrix? See, when I wrote down A as U sigma V transpose, another way of writing it is that let's just say that U sigma times V transpose. Let us just write it this way. So this is, let's say, N cross 10, and this is AK, 10 cross D, right? So this is a matrix. I can write, when I'm doing a low rank approximation of A, I might as well write it as a product of two low rank matrices, N cross K and K cross D, right? Therefore, and what we are saying is that fix K, fix the low rank that you're interested. What is the best low rank approximation of the rating matrix that you have? This is exactly the SVD problem. Exactly the SVD problem that we have been talking about, right? That all that I'll do is that I'll sort of calculate the SVD of the rating matrix. I'll take this U sigma V transpose. I mean, again, this would be, I would take only K of them. I would take K of them, and I would use this AK, which is the optimal low rank approximation of it, to fill out the remaining entries, period. Right? This is the baseline over which all this other work on recommendation system builds upon. And this is a very good baseline, very hard to beat. Okay. That here is the data that was in the Netflix data. They had 17,000 movies and 500K possible users. Therefore, the total possible number of ratings is 3.4 billion ratings, out of which only 100 million ratings are given. The rest are missing. The SVD approach is the following. The simple SVD approach, there are caveats to this, is that given this rating matrix R, which is 100 million entries of the 17K cross 500K, take the rank approximation. So K is a hyperparameter. You have to tune over these hyperparameters as usual. Figure out the right K, right? And take this low rank approximation of the rating matrix. Now this low rank approximation has all entries that are filled out. Use those as the predicted entries, period. Right? This is the SVD approach. What is the drawback for this? Any thoughts? First of all, is the SVD approach to recommendation systems clear? See, this is the most basic thing, because here I'm not looking at the cast of the movie. Here I'm not looking at any other movie information. Right? You could add all of that on top of this. But what is a caveat of, but what is the problem with this approach as of now? That is a very good question. That is a problem. But there are more basic problems too. That is also a problem. That is also a problem. You mean the complexity? That is also a problem, but that is doable. That is doable. That is doable. Huh? Should have a. But I could do this calculation offline and every night and then keep this updated or something, right? Something like that. All these engineering hacks you could do. Why? Why is that? No, that was given in the Netflix data. In the Netflix data challenge, the $1 million challenge, yeah. That is a very good question. Yeah. That is also a very good question. You're going towards fairness of this because is everybody equally represented? Yeah. Yeah. Yes. That is, this is true. This is true. All of these problems are true. All of these problems are there. What I'm saying is the more fundamental problem with even defining the SVD here. Because see, if you think about the matrix R, what is the matrix really? Matrix has some entries that are filled out, right? I don't know the rest of the entries. So basically, it's a matrix with missing values. What do I do with the missing values? Because define, so look at, so imagine that you're creating this in MATLAB. In MATLAB, you define the matrix. It's an n by a matrix. It's all entries are empty. You filled out only 10 of the entries, and then you ask MATLAB calculate an SVD. Won't be able to do it because the entries are not there. It will say that the matrix is not yet filled up unless it has some default value that it puts in all the entries. Let's say that MATLAB inside NumPy, rather than creating the matrix just by a collection of empty cells, you create the entries as NumPy.zeros. That means that every entry that you have not filled up is filled out with zeros. But good point. But then what is happening? See, look at the numbers. Out of 3.4 billion, only 100 million is real data. The rest of it depends on whatever sort of came in early in the morning to fill out these entries. For me, it could be 0. For him, it could be the majority of the entries. So therefore, whatever SVD comes out will depend on that majority date, sort of arbitrary data, rather than on the real data, which is 100 million. Right? This is a real problem. She's saying that the data that I have, I don't know how to define the SVD in this setting because it is a matrix missing entries. And therefore, there's a solution, of course. Right? We have to then, implicitly, we could put in something for every missing entry, but that is just an arbitrary thing. There are other things that people do. They say replace every missing entry by a row average, column average, all of that. All of these are heuristics. And some of them work sometimes, but these are not very nice ways of solving the problem. The right way of solving the problem is the following, right? Redefine your notation, redefine your loss function. See, my loss function was Frobenius norm, which was basically looking at reconstruction error per entry and including the entries that are not observed. What I'm telling you now is redefine your Frobenius norm to say that, okay, that these are the locations that I've observed, right? When you give me, if my original rating is Rij, if you give me a matrix, new matrix Bij, I will calculate the loss only at the locations that I've observed. at the other locations that I've not observed, this Wij, I'll set it to be 0 if Rij is unknown, which means that that will not figure in the loss. Right? So this is called a weighted Frobenius norm. And now we could ask the question that, can I get a low rank approximation just like the SVD according to this weighted Frobenius norms? Unfortunately, things are not as mathematically elegant anymore. So you cannot really take the original SVD and use it as such. However, you can use set up this problem. You can use gradient descent, and the original SVD you can use it as a very good initializer for this gradient descent. Okay. So this is the current status. I mean, one of, as in PS. Right. One other question is that how do you choose the K? As one of you are saying, and as we saw that typically there is no, I mean, there's really no nice answer. You do sort of cross validation, hyperparameter tuning, all of that, and sometimes in some pictures you can see a nice K, right? As in the cat picture that we saw, there's a huge drop right after the 10, right? So therefore, I could stick with K equal to 10, right? Because after that it's more or less flat. If your data does have such a nice structure, you should utilize that. If it does not have such a nice structure, then you have to use hyperparameter tuning. That's really all, right? I just want to give a gist of this, right? That PCA SVD is a set of methods to find out reduced rank or reduced dimensional representation of the data. Principal components are the same as the singular vectors, right, for the centered data. And a very useful data processing pipeline, some of it you will experiment with in the tutorial, is the following: is that if somebody asks you to cluster data, first think about is whether you need to take a low rank approximation of it, right? I mean, you might need to sometimes, right? If you're taking a low rank approximation of the data and then clustering it, kind of gives you a much better clustering. You will see that with the MNIST data today. That clustering the original MNIST data versus visualizing the sort of the PCA version of it versus visualizing another reduced dimensional representation, which is known as the TSNE, right? Version of it, and you will see the differences in the two. And this often outperforms clustering original data points. So again, I mean, there are a lot of caveats. There's a huge amount of research area in this. How to compute things faster? What do you want to do if you want to go beyond capturing linear structure? What do you want to do if you're interested in other notions of being close to the data, right? And all of that, right? Not these L2 norms or Frobenius norms. What else can you do? So that's all. Questions? Online attendees, webcam issues. Okay. Any questions from the online people? Yes. So that is collected data. That is not part of the model. So you would have to sort of engineer your data collection pipeline such that you understand something like how much time the user has spent on this, etc., etc. And based on that, you could try to then predict, yes, is the user seriously sort of interested in the movie or at the browsing? For instance, a very important pipeline in processing queries, search engines, is that they try to predict is the intent of the session. So these are called search sessions. You sit down in the search engine, you search for some things, you click, then you go away. So they do categorization of the search sessions to say that, okay, in this session, the user is interested to buy something. In this session, the user is looking only for some information. They search and there's all these different intents that are people try to figure out based on the user's behavior with the interaction with the system. Yes, you could do what you're saying. Any other questions? Okay. If not, then thank you. Let's have some tea then. Online last call. Okay. I guess not.